quick collective round of introductions. I'm going to encourage you to go onto LinkedIn and stalk our guests and link up with them. I'd like to quickly introduce Clarissa Phillips from Sydney Water, Rosario Dapra from Water Corporation in Western Australia, Patrick Bonk from Innovise, and Daniel Chow and Brent Robinson, who are joining us from Los Angeles, the Department of Water and Power. So that is our rapid round of introductions to our great panelists. And with that, I'm going to fade off into the distance and invite Clarissa to come up and share her story. Thanks so much, Clarissa.
Thanks, Adam. Hi, everyone. About 15 years ago, I worked in a really large engineering firm, and we just won a 10-year program of work with a large water utility. But to my team of very experienced AutoCAD users, horror, the whole project had to be delivered in MicroStation. My team really didn't want to lose their skills, and they didn't want to deliver this in MicroStation. Instead, they wanted to use the AutoCAD and convert to MicroStation. My manager, who had had enough of everyone whinging, wanted me to go to their PCs and remove AutoCAD and put on MicroStation. But naturally, I knew this wasn't the way to go. In the long term, we couldn't convert to MicroStation, and you really can't just delete AutoCAD and have MicroStation. So the way to go, I implemented a staged approach with training and so on. So the same needs to apply when you take everyone on their digital engineering journey. You need to apply this at a staged approach. In my presentation today, I will share with you my own personal experience, the good and the bad, in taking Sydney Water on their digital engineering journey. I'm hoping this will equip you with the strategies and skills to take your company on their digital engineering journey, whether you are a consultant working with a government utility or working as a utility employee. So my agenda today is going to go through what Sydney Water is up to, the Sydney Water approach to digital engineering, what are the current challenges, and what has been successful. So what has Sydney Water been up to? Sydney Water is the largest utility in Australia. We provide safe drinking water to over 5 million people in Sydney, the Illawarra, and the Blue Mountains. So we've got a lot of assets and lots of legacy systems built many years ago. And we're working on some pretty amazing projects too. We have designed Sydney Water's IoT program to enable the vision of getting ahead of the issue. We've deployed 3,000 sewer blockage detection services. We've deployed 2,300 digital meters to explore customer benefits and network benefits. We are using data analytics to capture our assets and predict pipe leaks. But only just using these standalone projects is not going to benefit Sydney Water in such a large way. However, by introducing digital engineering, we can bring all of this amazing data and information we're collecting and integrate this into our digital engineering models or digital twins and visualize this data information. Digital engineering will enable things like having a central source of truth for our data. We also want to have the right information at the right time. For example, using our data for planning our assets or predictive maintenance. So to start this digital engineering journey, we have developed a new digital engineering standard to guide our way through this at Sydney Water. So the Sydney Water approach to digital engineering. So we've got delivery, which I'll explain in the next slide, and we've got organisation, which is digital twins, and looking at a proof of concept to show that full life cycle benefit. We're also working with industry. We're working with WASA, and we're working with BM for Water, Australian Water Association, and of course SWAN. So next slide, please. So what we recently did is change the way that we plan and deliver our projects at Sydney Water by the introduction of P4S. P4S stands for Partnering for Success, and it includes 3 regional consortia consisting of multiple companies who have come together to provide design, construction, maintenance, and facility management services on a regional basis in the north, the south, and the west. We did this to drive innovation, efficiency, and increased certainty of delivery, which creates increased value for our customers. Now, it wouldn't be a government presentation without a graph, so I've added one in. Referring to the roadmap, as you can see, this is our staged approach for implementing our standard. And we're only at the start, we're only at year 1. So at the start of P4S, we appointed a digital engineering lead from each area to work in collaboration on building the digital engineering standard. And we agreed on some achievable implementation milestones and KPIs, as you can see. We also wanted a consistent approach to delivering our new standard. The delivery of the digital engineering standard in this staged approach, each year we mature, commencing with the standardising the way we work. In year 1, and then year 2, we go into collaboration, year 3, 4D, 5D, 6D by visualising, and then year 5, we get into the fun stuff by optimisation. So next slide, please. So what are the challenges? And there've been many, believe me. So because of these legacy systems, which has heaps of work around, just coming up with an asset data standard was really difficult. So what we did is we started up a project and got all those experts in the room that manage our asset data and, you know, work and started up a project to get this done. Another thing I did that was really helpful was set up a issues register, and pretty soon I learned that this issues register all pointed to the same thing, such as all these workaround systems and legacy systems. So the good thing about digital engineering, I know we can improve this. Another thing we did was start to try and do some asset tagging. Now this was quite difficult because of, you know, the standard data that was in our systems of Maximo. So what we've been doing is trying to come up with a consistent approach to tagging, and we got together with the RDCs and we're working with WASA and BIM for Water to come up with a uniclass system, which is a classification system for the water industry. The other thing you need to do is plan for those knock-on effects. So our document management system reads the metadata from AutoCAD, and then that goes into our asset management system such as Maximo and Hydra. Now, when we replace this with our 3D models, you know, what are we going to do? We need to plan for this and let those people know and try and come up with an interim system. Another thing you need to do is understand your business requirements. What do you want to see when you receive the workers' execution models? What do you want to do? What's your digital engineering twin need to contain? What level of detail do you need? So slide 6, please. Our success. So what we did is P4S, Partnering for Success. That's building a fantastic relationship with our consultants, delivering our digital models. And also working in collaboration, setting up strategic meetings and technical working groups to run through and nut out all those issues you might have with your digital engineering standard, with all those great specialists in the room. And I've learned so much from that. It's been fantastic. And also having our digital engineering proof of concept. This is going to be an amazing way to see how we can enable, you know, smart information management. And we're also very excited to announce today our Smart Cities Council Digital Twin Challenge. So watch this space. This is going to be something new and exciting that we're going to be working on. Next slide, please. So to sum up, remember, your key to success is use a staged approach and work in collaboration with everyone when you're building your digital twin. Thank you.
Clarissa, thanks so much for sharing that journey, and hoping that that resonates with many peers that are on the line listening in as well. So encouraging everyone to certainly reach out and connect with Clarissa. But let's not delay, friends. Let's get straight back into it. Let's head to Western Australia. And I'd like to invite Patrick and Rosario to share their presentation. Gentlemen, thank you so much. Over to you.
Thanks, Adam. Hello, I'm Patrick Bonk from Innovise, here with Rosario Zarpa of Water Corporation, Western Australia. Our brief run through today looks at how digital twin technology has been adopted and will progress through use cases in doing so. Next slide. So to articulate how best to align the core concepts of digital twins is to contemplate the time horizon in which you're solving your problem and relate that to the actual problem objective you're looking to solve. So digital twin use cases outlined in this figure have matured to a point where predictive alerts actively support responses to planned and emerging incidents in a given network. So this presentation, the concepts discussed here, were actually inspired by a lot of the talk in the industry around the trade-offs between data-driven and physics-based models. So if you refer to Swan's digital twin architecture, within the data analytics layer, you will see model types and their diagram with other key elements of the architecture. So it's from data integration, analytics, visualization, user experience, essentially like how the user interacts with the digital twin itself. So within the data analytics layer, you have data-driven models, and that can be anything from a simple variance function to determine a threshold exceedance on a single sensor. And then those data-driven models now progress through predictive AI, where AI recommendations, inform operators how to operate a given asset. So now the question here is, if AI is so advanced or has so much potential, then why would you use a hydraulic model that simulates the physics of the system? So the reason being is essentially sensors are not available in all parts of your network, and a live physics-based model allows you to test operational changes before you actually implement them in your network. And then, as you can see in front of you, with this kind of cohesive platform that's now in the cloud enables model types to share workflows where they are used to supplement each other, and then minimize the trade-offs associated with the model types. So over to Rosario, who will discuss Water Corp's application of the digital platform.
Thanks. So the Water Corporation is a very large water utility which provides water and wastewater services to more than 2 million people spread out across all of Western Australia. It operates a number of schemes. The main one, we call it the Integrated Water Supply Scheme, which serves the Perth metropolitan area. This area is quite extended and low density. And although it's quite young by international standards, it's starting to age, which prompts issues of performance and requirement for optimization. For this reason, this year, we have started a research and development project through the Water Research Foundation, where we partner with the Innovize to investigate how smart water network technologies could assist us in achieving some of our corporate goals, namely a reduction of leaks and bursts, reduction of customer interruptions, but also deferral of capital work and extension, where possible, of asset life. Moving to the next slide, please. These smart water network technologies consist of two components. The first one is a dashboard, which has got fundamentally an asset management kind of use. So it's meant to assist us in asset management decision. What it does is that it interrogates and queries field data as well as SCADA data to determine some KPIs in our networks. So what the first KPI we looked at was the ILI. So as we can show in the graph on the top, we determined this ILI on a time scale. In this case, we are reporting every month for our 4 study DMAs. And this was quite powerful for us because it showed us that the way we calculate it shows some seasonality in the behavior of the ILI, which means that we got some deep insight on how demand changes between summer and winter at night in our systems. On the other end, the fact that we can plot performance, so ILI performance of our study areas in a simple graph, it does really help us identify which areas perform worse than others and help us focus on some areas in terms of activities like leak detection and repair. The second aspect of that was developing a tool which could identify leaks as they occurred in the system. So we ran a field test where we actually opened overnight an hydrant, and we were trying to achieve approximately 10% of the minimum night flow for that DMA out of the hydrant overnight. And we were looking at seeing whether the business block we developed for leakage detection would detect that, which it did, as shown in the second graph. The interesting point here is that we were targeting a small magnitude of leak, which in our soil that are mostly sandy would probably go undetected for quite some time, which over time would determine quite a bit of a water loss. Moving to the next slide, we go into the second component of this technology, which is a live model. So the live model that we created, we use it fundamentally with the idea of managing pressure metered areas. So for 2 pressure metered areas, we use this live model to assist us in a modified operation where we would further drop pressure overnight to try and reduce background leakage. So we are still using these new settings, these optimized, if you want to say that, settings, because in the long run, we want to be able to collect enough data to understand whether background leakage is something that we are interested really in reducing, and if this is an effective way to do that. But the main element here also is that creating a live model means that we put an effort into creating a model which updates itself updates its controls from available SCADA, and also updates its demand in real time and predicts demand that is going to occur in the next 48 hours. With that in mind, the model doesn't really need a modeler anymore to update itself, and it can live in an environment such as the control room, where operators can use it to effectively plan for their own contingency and create their system change instructions without having sometimes to come to planning to seek our advice. And that would streamline really our workload. Moving to the next slide and back to Patrick.
Thanks, Rosario. I just wanted to give special thanks to solutions engineers Elin Afwang, Nathan Gertz, and Ollie Moravsky for their work on that project with Rosario. So progressing from predictions used with demand forecasting, as Rosario mentioned, to inform the operational models, we progressed to actual prediction with AI. So we now have projects that are utilizing model predictive controls. And this system is that the AI can essentially abstract out any process schematic, so water, wastewater, and treatment plants as well, into a real-time predictive model that accounts for changes in weather, how the environment changes, overall system changes in real time. Objectives that are set with the system, such as optimizing pump control schedules, are set to reduce energy consumption. And you can see in the figure on the bottom right side which data sources are inputs for the AI application itself. And the figure on the left is how the user actually interacts with the software, where predictive recommendations for optimal pump set point changes are visible on the dashboard itself. So the end user, the operators themselves, receive recommended control schedules for the operators to run a given set point for a particular asset, as well as set point changes are sent out via email alert for an alternative way to interact with the software itself. Outcomes we're seeing so far on projects of this nature are payback periods of the technology of around 6 months, and that translates into 15 to 30% energy savings. If we could just go next slide. So to bring this home, as we saw with Rosario's work with Water Corporation, they're establishing a digital platform that integrates data-driven models and physics-based model combinations for operational and asset management use. This figure shows how the user interacts with the software relative to those combinations of models we've been speaking to. And from a time horizon perspective, you're using the past, the historical data, this historical state of your network, and that informs the performance of the network using user-built workspaces with performance KPIs. You're looking at the present moment, the present time horizon, that's used to generate alerts based on incidents occurring in the network, which are then with the physics-based model used to generate what-if scenarios and contingency responses. And then the future scenario, the future time horizon, we forecast network demand that informs our operational hydraulic models. And now with AI, that provides predictive recommendations to the end user. From a cloud standpoint, what often inhibits technology adoption or getting projects of this nature off the ground is IT constraints. So speccing and sourcing your servers for storage capacity and compute power and resourcing. Cloud platform technology in the water industry, it's matured to a point where scalability of these systems is enabled for the compute power and the shared services between model combinations that are now exposed to a single workflows for the end user. So that's it from us, and thanks so much.
Patrick and Rosario, thanks so much for that presentation. As a tag team, you did an excellent job. Thank you again. And in the same format, I'd like to now invite Daniel and Brent to step on up and share what they're doing over in LA. Thank you, gentlemen.
All right, thanks, Adam. Hey, everyone. First off, I just want to thank the SWAN coordinators for inviting us to speak here and putting this thing together. Looking forward to hear more ideas from the latest and greatest companies here. Definitely a lot of relatable points in that last one. But without further ado, my name's Daniel Chow. I'm an electrical engineer with LADWP. One of the relevant projects I'm working on is the wind project here, but I'll talk more about that later. For now, I'll just introduce our biologist, Brent Robinson, who will start us off with just a little bit of background.
Thanks, Daniel. Hello, SWAN attendees. My name is Brent Robinson, and I'm a biologist with the LA Department of Water and Power. I wanted to start off with a little bit of background for the impetus of the model from a biology perspective. We're on the right slide, good. What we have here is a schematic of our aqueduct system that connects the city of Los Angeles to source waters around the Owens Valley Basin. There's about 7 reservoirs and lakes, over 350 miles of open and closed channel aqueduct. There's DWP power generation plants and facilities and small towns all along the way. So that makes for numerous sample points in and around our reservoirs and along the aqueduct and at some of these facilities as well. The water travels a long way before reaching Los Angeles, and those distances can present a challenge when it comes to monitoring, interpreting, and delivering data, especially when you're trying to affect fast operational changes. My job as a biologist is to provide water quality data to our operations group that are actionable and easy to interpret. Things like algal monitoring and bloom impact, the realization of our algal monitoring plan initiatives and the execution of that plan. We recommend and execute treatments, public notices, etc. We want to be proactive and be in a position to leverage the data collected in the best, most effective way possible, whether that be to better understand the development of our algal blooms in our reservoirs, or to know where to issue a bottled water notice due to an algal toxin detection, which has definitely happened in the past. Next slide. So this slide is just basically to show some of the historical methods that we've used in the past to collect and document data. Generally, our group collects data. It's entered into a database to be queried for the constituent or parameter of concern. But what we really needed was a system that would reflect all the inputs that describe our source water, presenting the entire landscape in one place. A system that is data-driven, could be modified, and also included some visual aids for trend monitoring. Basically, we were trying to build a digital twin or dashboard of our utility. And in doing so, we're hoping that we bring some of these traditional data collection methods into the 21st century. And with that, I'll let Daniel introduce you to what he and his team have built.
Thanks, Brent. Okay, thanks. Yeah, so this is Daniel again. I just want to start off, before we get to the digital twin, just a little bit more background on our motivation behind this project. So as mentioned briefly at the start, I'm one of the developers of the so-called WIN project here, or the Water Information Network project. And this project is basically our water system's smart utility initiative. One of the main ideas, the driving forces, is that many tasks that we do or want to do become a lot easier when our data is centralized and it's accessible and we're using the right sort of software. So what has happened throughout the many years of our company's existence is that databases and platforms all fully matured on their own, totally separate from each other. So part of what we're doing as the WIN project is bringing these databases together to achieve end results like the one we're covering today. So circling back here though, back to algae monitoring, we as the WIN team sat down with our internal water quality division and figured out just what kind of data is relevant and where that data is kind of living within the department. So for this model specifically, we decided to incorporate our internal LIMS water quality data, our SCADA systems for things such as flow rate, and NOAA weather data for local temperature. And all that goes into a really capable central database. We're using OSIsoft's Pi server. And once that's all in, the Pi server comes with a great set of visualization tools and integration tools that we can interface with our data sources and analytics too. So once it's all in, we can achieve things such as data accessibility across our company, alarming, dashboards, and some analytics too. So next slide, please. So here is just some screenshots of what our end user, or in other words, Brent's group, might end up using. So if you look closely, what we have here, it's basically a process flow model or format of a large chunk of our water system that updates in real time. So what we would have normally data that's living separately in our company is all finally together on one screen, and it's just continuously updating. So it just gives operators or users a much better picture as a whole. We can furthermore click into a reservoir. So next slide, please. And clicking into a reservoir would bring us to another page on the left here. And what's happening currently on this screen at our Long Valley Reservoir is that our total microsystem level at this time happened to be within the medium threshold, which placed this site at the time at a moderate risk. So the necessary personnel can be notified immediately. And clicking the trend view button at the top there just gives us a more historical reading of the site. And the only reason I put that screenshot there is to illustrate that we have a lot of data coming in throughout the years that we are looking to leverage and use, or in other words, feed into a predictive model. So I want to turn it over to Brent, who will talk more about where we want to take this, but thanks.
Thanks, Daniel. So just to recap, I anticipate this tool helping my group in the visualization and understanding of our collected data. They can definitely help us in our algal monitoring, plan coordination, and rollout. And just basically to allow us to make better operational recommendations and assessments. Instead of having to compile all these data through successive queries, we now kind of have a one-stop shop for everything we need to know and see and visualize. This model is it's just the first step. We definitely have plans to expand it and build it out in the future. And that build out could include technologies like remote monitoring sensors, which we're currently testing out, some remote monitoring buoys that will allow us to have some real-time water parameter results that could be added to this model. We also do algal toxin mRNA PCR, qPCR analysis, and that could be added to this model as well for additional predictive purposes. Obviously, the end goal is to have a fully predictive model, which is the holy grail, of course, and it's something that we're definitely trying to achieve. But in water quality, our ultimate goal is to provide the end user, which is our customers, with the highest quality of water possible. And this tool can help align us with those intentions for sure. And thank you very much.
Daniel and Brent, thanks for sharing that with us. And for all of my guests on the panel, you've done a stellar job at keeping your presentations quite tight. We do have around about 9 minutes to go. I'd like to encourage our audience to use the Q&A and chat function in the platform to share any views or questions that they have. I have 3 questions. I'm going to reserve those for the moment. One has come from the audience, and I'm going to go straight to that one. And the question is not necessarily directed at anyone, but I'll open it to the panel. Anyone can respond to this. What was the most valuable learning made during your digital twin journey so far? Let me direct that one to start with. Let's go with Sydney Water. Clarissa, do you want to touch on that one first, and then we'll sort of go around the group?
Yeah, so the valuable lesson for me was, working in collaboration and getting those technical experts on board with P4S. Like, if I didn't have them, the people actually using the software and, just coming up with a model name, what we had in the standard was too long. And so we couldn't actually use it. And if we didn't have those technical experts to work with, we'd look like idiots basically when we implemented this and put it on our website and, implement it to the world, So that's working with our consultants has been key for us.
Yeah, excellent. Rosario, can I head straight to you for Water Corp? That question, what's been the most valuable learning so far?
Well, we are in the early stages of the deployment, because this was a research and development project. I think the key element now is that we need to instate a bit of a culture towards the use of these technologies, particularly across departments which operate a bit in an old-fashioned way. So this is where our effort now needs to be: convince them to use them and show them that they can streamline their own workloads and procedures in a more effective way.
Yeah, excellent. Brent, Daniel, how's the Department of Water and Power gone in terms of its most valuable learning so far on your journey?
Well, I think I would say for myself, actually, it's usually the scope of work that I do as an electrical engineer is obviously totally different than what we were doing on this project. So I kind of was living in a bubble, and working on integrating a bunch of different data sources within our company just gives the perspective of what we do as a whole just a bit better. And I think I can say the same for the users of our Pi Vision platform, that they can see what's going on outside of just their, scope. So, or at least I hope that's the case. So, thanks.
Brent, you got a response on that one? You're on mute. You made me say it, but Brent, you're on mute.
Sorry about that. I would just say that, the excitement from my group is going to come from visualizing all these data in just one location, and working with, the engineers, making this come to fruition is been a pretty exciting journey in and of itself. But I think it's been a long journey, and actually seeing the end result, come together like it has been really rewarding.
Yeah, excellent. Patrick, I wanted to ask you a question as sort of the private sector rep here on the call, advisor, and working, with clients on the demand side. I picked up in one of the slides that you were speaking to where you were highlighting sort of a values-based return on investment, something, I think it was like 6 months or something thereabout. Can you share some views on where you think the marketplace is at on the demand side in terms of appetite, realizing the value to invest in this capability we call digital twin?
what do you mean by appetite? Are you referring to the marketplace in terms of their willingness to adopt AI?
Exactly. Well, yeah, exactly. Like, are you having to really push it and really convince? Is there a demand there that you can't keep up with? Where are we at with supply and demand and valuing and appreciating the capability?
I think it's a matter of taking what's a really broad-based term, such as artificial intelligence, and distilling it down to actual results that can be achieved. And then as we have more projects on the ground, achieving results like, say, 15 to 30% energy savings or a certain cost savings. Like when we're able to say, or guarantee an ROI of, say, 6 months on that technology, the conversations are much easier to have. And just based on operational savings, we can do an initial assessment on the system. The data science team can conduct that assessment and actually model out how that's going to look like over that first 6 months and, you know, post 6 month period, and how that's going to look like when it's scaled beyond the pilot side of that project. So it's a matter of having success on the ground and cutting through the noise as well, because AI can be a lot of things. Yeah.
I'd imagine so. Okay, thank you for that. We've got another question that's come through here from the audience. So for the LAWPD WP team, Daniel and Brent, the question is there an analysis done on the LIMS and sensor results on the LA pipeline? If yes, was it done through technology or manual means? Who wants to have a go?
I can take that one. So yeah, there is a pretty simple analysis that we're doing on the bare data that's coming into the Pi server, coming from LIMS. And if you recall in the presentation where we were kind of assigning risk levels to the site, we just took in the water quality data, such as total microsystem level and chlorophyll A, and kind of crunch the numbers within the Pi server. So to answer your question, it's through technology. None of it was manual. And through that, we were able to assign a site risk level. But we want to move to like a more advanced form with prediction using the same sort of data. So yeah.
Okay, excellent. Friends, I've got 120 seconds left here on my clock for this session, so I'm going to draw our questions to a close there because I want to hand back over to Greg as well. I think Greg's still on the line as our session MC, but for now, I'd like to thank sincerely Clarissa and Brent and Daniel and Rosario and Patrick for joining us and sharing their digital twin journeys. Thank you so much for sharing. I hope our audience has enjoyed that. And if Greg Ryan is still there, Greg, are you still there? You doing a final wrap? Maybe not. Okay, he's delegated that responsibility to me. I'll just pick up the reins and bring this this session to a close. So I hope you've all had a fantastic couple of days and sessions with the Swan Network sort of event. Lots to learn, as we heard at the introduction. Videos are going to be available. Recordings of these sessions will be available. Lots to go back into and watch at your leisure. But for now, I'll sign us off from this session. Thanks so much, everyone. It's been a pleasure.
Thank you.
Thank you.
Thank you, everyone.
Okay.
Cheers, well done.